Alright, hey, what's up folks? Welcome back to another video. It's your favorite talking mustache. Today we're going to be looking at some practice problems for carboxylic acids and their derivatives. I do have a playlist that discusses some reactions involving carboxylic acids and their derivatives. This will be part of that playlist, but it's more so designed to be practice for carboxylic acids. How do we make them? And then once we make them, what can we do with them? So that being said, let's go ahead and dive right into it. Now, before we get started, it's very important that I cover two helpful tips, right? So number one, whenever you're dealing with anything in organic chemistry, always identify what is on your starting compound and what's changing in your final compound. This will make life so much easier because now you have an indication of what sort of reaction you're going to need to use to cause that transformation or cause that change. Once you identify what's changing on your starting compound versus your final compound, now you can begin to sift through all the reactions that you've practiced and memorized in your head and be like, okay, what's the general reaction? Does it work for this particular example? I do have a video on my channel that essentially provides you with a systematic guide, a systematic workflow, 1, 2, 3, 4, 5, 6, that'll help you study and memorize for any mechanism or reaction in organic chemistry, making it a whole lot easier to remember these things down the line when you're solving some practice questions, as we'll see here today. With that being said, let's go ahead and dive into the first practice question. So let me go ahead and get the laser pointer going. And it says here, practice question 1, convert toluene, this, into a carboxylic acid, so benzoic acid over here, using the following step. So we're asked to convert toluene into our benzoic acid, but we need to use some sort of reactions or some set of reagents to get to this middle compound, and then we convert that to our benzoic acid. So let's go ahead and begin breaking down the question. This question would have been a whole lot easier if it just told us convert, toluene into benzoic acid. That's very simple. We can do that because toluene is, the CH3 is technically an R group, so we could have used something like potassium permanganate oxidation. Very simple. But the fact that it's forcing us to use this sort of amide salt in the middle makes it seem a little bit more difficult, but as we'll dive into right now, it's actually not that difficult at all. So since this is sort of our bottleneck, let's go ahead and start with this compound here in the middle. We can see that we need to somehow convert this toluene into this amide here in the middle, okay? And what else do we see? Well, we have we have a carbonyl group over here, and we have Cl-, which means that we may need to use some sort of reactions involving acyl chlorides, okay? Because remember, an acyl chloride is just RC double bond OCl, okay? And we know that we can convert acyl chlorides into amides, which is what we have here, using what? Let's go ahead and just go to the next part here. Using amines. We can convert acyl chlorides into amides using amines. Okay, this basically here just separates the ring from the actual group that we're interested in. Okay, so we can convert any acyl chloride into an amine, okay, into an amide using amine. Okay, this is the general reaction. But for our purposes, we're only really interested in converting some acyl chloride into the following. Okay, where all of these R groups are essentially CH3s. As we can see here, this is a CH3, this is a CH3, and this is CH3. So we've successfully identified, okay, we can convert an acyl chloride into this amide using NCH3. So NCH3, CH3, CH3, there's 3 of those. Okay, now the next very important question is, well, how can we convert, our toluene into an acyl chloride? So the question here becomes, how can we convert our toluene into an acyl chloride, in this case benzoyl chloride? But we're really only interested in converting this CH3 into this acyl chloride. Now, let's just think here for a minute. I wrote down a couple of questions. We have our benzoyl chloride that we converted to an amide, last slide, okay? We now need to find what reaction we can use to convert this benzoyl chloride to produce toluene to convert toluene into a benzoyl chloride, okay? What reaction do we know? Well, let's think. We know that we can produce acyl chlorides from what? From carboxylic acids. Great. Can we convert our toluene into a carboxylic acid? Well, yes. All it is we use potassium permanganate oxidation, okay, by converting this CH3 into a carboxylic acid. And then we can convert this carboxylic acid into our acyl chloride using thionyl chloride, SOCl2. So this is how you need to approach the questions. Notice how we had to sort of fragment it and break it down and be like, It seemed like we were all over the place, but we're just trying to break down the question into fragments and then reassemble everything together into a more coherent synthesis or plan, if you will. So that's how we do it. So we can convert our toluene, okay, into a carboxylic acid using KMnO4, OH minus heat, and then H3O plus. That converts it to a carboxylic acid. This carboxylic acid can then be converted to an acyl chloride using SOCl2. This acyl chloride can then go ahead and react with our NCH3 to produce our amide. Great. Once we have our amide, then now the final question is, okay, how can we convert this into a carboxylic acid, which is essentially the question, or the initial question from the beginning. Now, we know that we can convert carboxylic acids, we can convert amides into carboxylic acids using H2O, H3O plus, or a base. So that's what the reaction is going to be. And once we fill that out, we have successfully answered the question. So that's how you can convert your toluene into a carboxylic acid while being mindful that this is the middle step that you must pass by. It would have been super easy if it just, if it asked us, like I said, to convert our toluene into a carboxylic acid, because then very easily we could have just reacted it with KMnO4, OH minus heat, and H3O plus. But the question posed that limitation posed the limitation of forcing you to go through this step over here, so that the examiners, if you will, referring to the examiners, can test your ability to think outside of the box. Okay. Next question here that we're looking at, practice question 2, says determine the final product. Well, let's see what we're dealing with. Can we identify what compound this is? We can see that we have a carboxylic acid on one end, and here we have an OH group, and we're given H3O plus. So, can we maybe label the carbons? Well, yes we can. This will give us a δ-Hydroxy acid, because this would be your alpha carbon, this would be your beta, this would be your gamma, and then this would be your delta carbon. So this is a δ-Hydroxy, referring to the OH group here, acid referring to the carboxylic acid. We know that in the presence, when we have a d'hydroxy acid, in the presence of H3O plus, we're going to have a cyclization reaction. And this cyclization reaction is going to proceed as follows. You're going to have the lone pairs on the OH group, or on the d'hydroxy group, come in and attack your carboxylic acid. This will go on to form a 6-membered ring, as shown over here, and that 6-membered ring is a δ-Lactone. Now, if it seemed like I moved very quickly, well, that's because I already have a video discussing this mechanism in depth, how to approach it, what the numbers mean. So if you'd like, I'll have another one of those video cards pop up on the screen so that you can watch that video on converting d'hydroxy acids into δ-Lactones. I think there is a typo here. D'hydroxy acid forms a δ-Hydroxy lactone. Sorry, I should correct that. Via intramolecular cyclization. Now, moving on to question 3a. Whoa, this looks a little bit difficult. It's not. We just got to break it down and approach it step by step. We're asked to convert. We're starting with 4-ethyl hexanoyl chloride. Okay, so we have some sort of acyl chloride. That's what we're really dealing with. We're asked to react it with NH3, and then whatever that product is, we react it with POCl3. And then whatever that product is, we react it with H2 and Rani nickel at 140 degrees Celsius to produce some product. And then we can also use the product from the POCl3 reaction, reacting it with D-Bal-H to produce something. So it seems like there's a lot going on, but let's just start one by one. So we're reacting our acyl chloride with an amine. Okay, we're reacting our acyl chloride with an amine. And we know that reacting acyl chlorides with amines produces amides. So we can basically fill that in. Let's go ahead and draw our amide. Perfect. Now we're reacting our amide with POCl3. Okay. Whenever we react an amide with POCl3, we're converting, and the amide has to be unsubstituted. Okay. We're converting that into a nitrile. So C triple bond N. Okay, perfect. We have our C triple bond N over here. Now, let's start off with this branch up here. We're now going to reduce this nitrile using Rani nickel H2, so hydrogen gas at 140 degrees Celsius. We know that this reaction does what? This reaction will reduce our nitrile into an amine. Okay, and that's what the amine is going to look like. Now, the other reaction will involve D-Bal-H, okay, and whenever you react a nitrile with D-Bal-H, you should know by now that this will produce an aldehyde, okay? And just like that, you have successfully gone through this problem. This comes with practice. The more you practice these questions, the more you sort of revise the general reactions and equip yourself with all of the reactions up here, then and only then will you be able to approach these questions very easily and very smoothly. Okay, on to the next question, 3b. Okay. Now it says, for the step involving phosphoryl chloride, POCl3, provide the intermediate structure that forms between POCl3 and the amide. Okay, so this is interesting, but not difficult, because the only way you can solve this question is if you have practiced the mechanism a handful of times. Now, to answer this question, you'll need to draw the intermediate, okay? And again, like I said, you're gonna have to practice this a few times before you understand what the intermediate looks like. But essentially, this reaction begins by the amide, where is it? Yeah, it involves a reaction between the amide and the POCl3. Now, the amide will begin by building a double bond over here, which will force electrons from the C double bond O, from the carbonyl group, towards, why did I pronounce that weird? Towards the phosphorus over here. This will cause the P double bond O to break and the electrons collapse over here towards oxygen, forming O-. Putting everything together, this is what our intermediate looks like. And again, the only way you could have really done this is if you could have answered this correctly is, one, if you're very lucky, okay, let's be frank, and two, if you have practiced this enough times. Obviously, you don't want to just walk into an exam based on luck, and you really want to practice this. So the more times you practice this mechanism, the better you will do. Okay, next slide. Perfect. Question 4. Question 4 is asking us to outline the synthesis for the following compounds. Outline the synthesis for the following compounds. So here we're starting off with some sort of carboxylic acid. Okay. And we have A and B. So some sort of set of reagents or some set of steps for A and some set of steps for B. And we need to convert it over here to what seems like an α-Hydroxy acid. And here we have an α-Amino acid. So that's step 1. You need to identify what are you converting. So let's start up here, up top. We are going to essentially, we need to be converting this to an α-Hydroxy acid. So this is the alpha carbon labeled in red, and this is our hydroxyl group OH, so that's why we call it an alpha-hydroxy acid. Now, let's pause. Now, in order to add an OH group to the alpha carbon, we're going to first need a good leaving group, because OH can come in and kick out and push a leaving group. But we need a good leaving group. Now, we need to think of what are the good reactions that we are aware of that enable us to add a good leaving group to the alpha carbon. Well, what are good leaving groups? Halogens. Okay, great. We know that halogens are good leaving groups. Awesome. What reactions fulfill those criteria? Fulfill that criteria. Enable us to add some sort of good leaving group, such as a halogen to the alpha carbon, and enable us then to replace it with a hydroxyl group, so forming our alpha-hydroxy acid. Well, the only answer, not the only, but the best answer in this case, is the HVZ reaction, the Hell-Volhard-Zielinski reaction, which involves the use of PCl3 and H2O to form an alpha-chloroacid. We know that chlorine is a pretty good leaving group. And now we can very easily kick out this Cl and replace it with OH- using NaOH and H2O. So the critical step here was what? Forming our alpha-chloroacid, which then reacts with NaOH and H2O to kick out the Cl and have our OH at that alpha position. Now, carrying on, now that we have our alpha, actually, let me go back to the question. Remember, the question said the following. The question said, we want to form, we just did this part up here. Now we want to do the bottom part down here, which is replacing the, we're just adding an NH3 plus group to the alpha carbon. Here, okay. So now we want to essentially still use the same alpha chloroacid, but we want to replace the chlorine here with NH3 plus. We want to replace it with NH3 plus. How do we do that? Well, we can essentially add 2 molar equivalents, okay, of NH3. If we add 2 molar equivalents of NH3, we then go ahead and form our alpha amino acid. Again, the critical step here was what? It was getting rid of this alpha hydrogen over here, replacing with an alpha chloroacid or an alpha bromo acid, any good halogen, which is a good leaving group. And then with that, we can react it with NaOH and H2O to form our alpha hydroxy acid, or 2 molar equivalents of NH3 to form our alpha amino acid. Now the next question is question 5, and it says, what will the most stable product be? What will the most stable product be? So we have some sort of, okay, we got a ketone over here, we have a carboxylic acid over here, and we're heating it, okay? Let's go ahead and start off by visualizing, drawing this a little bit better, redrawing it so that we can better visualize what is happening. Well, once we redraw it like this, and you'll see why I drew it like this, is we can clearly identify that this is a beta-keto acid. Beta carbon, alpha carbon. The beta carbon has the ketone, the alpha carbon has our carboxylic acid group. And we know that whenever we have beta keto acids and we subject them to heat, 150 degrees Celsius, 160, it's just heat, okay? They will break down to release CO2 and ketones and enols. Now it's asking us to draw what the most stable product is. So let's first go ahead and draw what the breakdown is going to look like. So we're going to have these series of exchanges. We're going to have decarboxylation. Okay, this is a decarboxylation of a beta keto acid. That's the full reaction name. And we will produce our keto-enol tautomers, and we're going to have tautomerization. Now, what do we know about tautomerization? The ketone form is generally the most stable form, and in this case, that is true. So we're going to go from our enol form to our ketone or keto form, and that's going to be the most stable form. That's going to be the form that will predominate in solution. Practice question 6. It says, outline a synthesis for the following compound using methyl isocyanate. So we're asked to convert methyl isocyanate into this weird ring structure. Okay? So let's go ahead and step 1 by identifying what this final compound is. Do we see any familiar functional groups? If there's a functional group that we recognize, can we think of any reactions that we could potentially use to synthesize our product, starting with, again, methyl isocyanate? All right. Well, we can clearly see that we're dealing with a carbamate functional group. This is the general reaction for a carbamate functional group. The question now becomes, what reactions exist, okay? What reactions exist that we can use to synthesize carbamates, but also we need to use methyl isocyanate, because that's what the question is saying. It says, using methyl isocyanate, convert it into this. Well, we know that this thing over here is going to have the carbamate functional group. So let's think here. Yes, we do know reactions that we can use to produce carbamates starting with isocyanate. And that reaction is using isocyanates plus alcohols to give us carbamates. So we have our isocyanate over here, we have our alcohol, and we can produce what? We can produce our carbamate. Well, this is great. We've done basically 50% of the work, or 90% of the work. We know that our isocyanate is just what? Methyl isocyanate. So we replace this R group with a methyl group. Now the only thing left for us is to identify what this OH is. Well, how am I going to know what alcohol to use? Well, let's go ahead and look at the final structure for our compound. This is the final structure for our compound. We need to somehow use some sort of alcohol over here. We have our methyl isocyanate. We can see if you just, let me get the pen going here. If you just snip right here, snip, we can see that this, basically we could insert an OH group over here, right? And then that would form our alcohol. So let's go ahead and erase everything. We can see that that right there, if we just insert a hydrogen, that forms our alcohol. And then we can effectively just use the following alcohol. And bada bing, bada boom, we have synthesized our methyl, we've converted our methyl isocyanate into this carbamate functional group. This is actually called Sevin or Sevin, using 1 naphthol. And just like that, we have successfully converted our methyl isocyanate into Sevin using the alcohol right there. Yeah, that's it. That's the end of today's video. Just 6 practice questions for you. I hope it helped. Hope you found these beneficial. Yeah, I have really nothing else to add. I suck at ending videos. I don't know. Perks of having a mustache. You have a great mustache, you make great videos, but you can't really end them because you love talking to people. So yeah, take care everyone. Hope this was helpful, and best of luck. Take care.